All right, welcome to the afternoon session on K2. This session is going to focus on materials taken broadly, and we're going to begin with a talk from Will Kirby. Will, are you there?
Yes. Hi. Can you hear me?
Yes. Well,
great.
So please take it away, Will.
Okay. Thanks. So hi, everybody. It's great to see three of you. Yeah, I guess the cat's out of the bag. I'm not Peter Love. Unfortunately, Peter recently came down with COVID. It is a mild case and he's going to be fine, but he was not feeling quite up to giving the talk. So you've got me instead. So surprise. Anyhow, I'm Will Kirby. I'm a grad student of Peter, and I'm going to be talking about the same thing he was planning to talk about, which is this algorithm called Contextual Subspace Variational Quantum Eigensolver that we developed along with Andrew Tranter. And there's a bunch of names on this slide as well, because this line of work has recently or subsequently been taken over by Alexi and Tim, who are grad students of Peter Coveney at UCL. And they've updated the algorithm and are working on building up to an actual demonstration on a quantum computer. So stay tuned for that in the future. They've done really nice work that I'll talk about a little bit at the end. And lastly, before I get started, I did want to just give a heads up that I'm probably not going to use the whole time slot. And so there will be plenty of time for questions. And I encourage you to jump in and ask them during the talk if there's something that's confusing. Hopefully I can hear people who ask questions from in the room, but if not, maybe somebody can help to coordinate that. Okay, so let's get started. I'm going to be focusing on two main topics in this talk. The first is variational quantum eigensolver, or VQE, which I'm sure most of you know well. It's the hybrid quantum classical algorithm used mainly for estimating ground state energies, sometimes excited energies as well. And it's possible to run this on pre-fault tolerant and even to some extent existing quantum computers. And the second main topic is contextuality, which is a feature of quantum mechanics that we'll get into shortly. But basically, this feature distinguishes quantum mechanics from classical mechanics. And it's not the only such feature, but it's the one we're going to be looking at how to exploit. So our goal in this work ultimately became to use to our advantage the structure of contextuality that can appear in variational quantum eigensolvers. So first, well, I'll have three main sections. First one, we'll talk about contextuality, what it is, and how to test for it in sets of Pauli operators. These sets of Pauli operators are going to correspond to the measurements that we performed during our VQE procedure. So we're going to be focusing on VQE that uses Pauli decompositions and Pauli measurements. This is pretty typical, but there are other versions. So just to highlight that that's the version we'll be looking at. And so then in the second main section, I'll discuss what it means for a VQE instance when the corresponding Hamiltonian is non-contextual, which means that the set of Pauli terms in it are non-contextual. And non-contextual is going to mean that this feature contextuality that should be distinguishing the quantum algorithm from a classical algorithm is not actually present. So we'll show that this means that in this case, we can replace the quantum objective function with a classical one. And then finally, in this last section, I'll talk about what we can do when the Hamiltonian is contextual, which is true in general. And this will lead to this hybrid algorithm, contextual subspace VQE, where we're going to be partitioning the Hamiltonian into a non-contextual part that will simulate classically, and a contextual part that will simulate on the quantum computer. And generally, simulating this contextual part on the quantum computer will use fewer quantum resources than we would require to simulate the full Hamiltonian. So first, let's quickly review how VQE works. We want to find the ground state energy of some Hamiltonian H, which we decompose into a linear combination of Pauli operators P in some set S with some coefficients H sub P that are real. And the way the VQE algorithm works is on the quantum processor, which is doing this iteration step down here. We prepare NZ states and separately estimate the expectation values of each Pauli term by repeated preparations and measurements. And then we classically recombine these to find the expectation value of the full Hamiltonian. This is a very, very rough scheme. You can do clever things like combining Pauli measurements, but we won't worry about that too much. Basically, we're just trying to build up estimates of all of these Pauli operators in the Hamiltonian. So once we have the expectation value of the Hamiltonian for a given ansatz, or an estimate of it, we use that as an objective function for a classical optimization over the ansatz parameters, attempting to minimize this expected energy. And so since the expected energy is lower bounded by the true ground state energy, this yields a variational estimate of the ground state energy. So we want to identify what separates this algorithm from a classical algorithm. That's sort of the high level, or a high level starting goal. And we're going to focus on the set of measurements, the set of Pauli operators that show up. Because the problem that we're trying to solve in VQE is defined by the Hamiltonian. And on the quantum side, what this determines is the set of measurements that are performed. And one can also, it's worth saying, consider how quantumness can appear in the ansatz. But that's not what we're going to be focusing on, although it is an interesting line of study. We're going to be focusing on the objective function. So basically, we want a means for identifying quantumness, which for us is going to mean contextuality in the set S of Pauli terms in the Hamiltonian. Okay, so to get into thinking about contextuality of sets of measurements, suppose we want to construct what is essentially a realistic hidden variable model for S. S is the set of Pauli terms in the Hamiltonian. Our model is going to consist of two main pieces. The first piece is going to be some set of joint value assignments to S, meaning we're assigning plus or minus 1 to each one, because those are the eigenvalues of the Pauli operators, so the possible values that they can take upon measurement. And we can think of these joint value assignments as something like phase space points for the model. And in our classical realistic interpretation of the model, they would correspond to the underlying classical real values of the observables, if you will. So then the second main piece is going to be a set of allowed probability distributions over these joint value assignments. And in the realistic interpretation of the model, these would represent our state of knowledge as the observers of the underlying values of the observables. So these probability distributions are going to replace quantum states. They're playing the role of predicting probabilities for observable outcomes. So in this model, something like an uncertainty relation that prevents us from simultaneously measuring the values of two observables that don't commute is interpreted as a limitation on the probability distributions that are allowed, meaning a limitation on what the observable is able to measure or know, rather than as a limitation on the underlying reality of the values of the observables. And just to be clear, this type of model, we're going to be showing when you can or cannot build such a model. So this isn't always possible for quantum mechanics, but this is the type of thing we're trying to construct. So as an example, if our set of measurements is just the single qubit Pauli operators x, y, and z, then the joint value assignments are the 8 possible assignments of plus or minus 1 to these, which are, we can think of these as like corners on a cube. And as probability distributions, we can think of the corners of the cube as representing probability 1 for each of these joint outcome assignments. But we know that x, y, and z, all of these don't commute, they all anti-commute. So we can't actually know their values simultaneously. So we expect the probability distributions corresponding to physical states to be bounded away from the corners of the cube. And this again is supposed to reflect a restriction on what we as the observers are able to know, rather than a restriction on the underlying reality of the observables. And so indeed, in this case, we find that the set of possible probability distributions is the sphere that's inscribed within the cube, which turns out to be just exactly equivalent to the block sphere. I won't get into that, but it's sort of a nice little fact. So any physically possible probability distribution corresponds to a convex combination of the probability distributions that live at the corners, but the allowed possible convex combinations are the ones inside this sphere. So this is a classical realistic hidden variable model of the type we're looking for Pauli measurements on a single qubit. And it's been well known for since long before our work that such a model is possible for one qubit. So this is not too surprising that it should be possible to cast it in this way. And so this definition of a model brings us to an initial qualitative definition of contextuality, which is that a set S is contextual when it is impossible to build a model of this kind for it. So we've just shown that a single qubit on its own is non-contextual. And we're in fact going to narrow our focus to strong contextuality, where we only ask whether it's possible to even set up the joint value assignments in a consistent way. These are going to turn out to be equivalent in our case, but in general, they're not. So worth noting that. Okay, so how could we end up with a situation where building these joint value assignments is not possible or violates causes some kind of inconsistency? Well, the consistency constraint that we're going to be thinking about is called inference, or it's called various things, but this one is pretty typical. And the way inference works is as follows. Suppose we have an assignment of values to our set S, and suppose P and Q are some pair of operators in our set. So these are just two Pauli operators and they commute. Our model, our requirement that we demand of our model is that it has to reproduce the predictions of quantum mechanics for the observables that it describes. Any observables outside the set, there's no obligation that our model behave nicely for them. It doesn't have anything to say about that. But it has to reproduce quantum mechanics for P and Q because P and Q are in the set. And the product of PQ is itself a Pauli operator up to a sign, and it commutes with P and Q. So our observer could, if they chose to, measure P and Q simultaneously since they commute and obtain the values assigned to them, which are both plus or minus 1. And the observer could then infer from those values the value that must be assigned to the product PQ. So for example, if we had Pauli X acting on each of a pair of qubits, I'm going to be suppressing tensor product signs. I don't think this will ever be ambiguous, but if it is, feel free to ask me about it. But so this means like Pauli X tensor identity and identity tensor Pauli X. So from this pair of single qubit Pauli operators, we could infer, if we had an assignment to them, the value of their product X tensor X. And we can visualize this inference with a little tree like this, where the parent node is the product of commuting child nodes. So we're going to be building up larger trees out of small trees of this form, and that's going to be the rule. The parent node has to be the product of the children, and the children have to commute. And this brings us to a more technical definition of contextuality, more precise, which is that the set S of Pauli operators is contextual if and only if any joint value assignment to S necessarily violates some inference relation of this kind. So it's important that it's any joint value assignment. Here, for example, there are some value assignments that violate the inference relation. So for example, if I assigned +1 to each of the single qubit Paulis and then -1 to their product, that would be inconsistent. But there are plenty of, well, there's 4 possible assignments that do satisfy the inference relation. So +1, +1, and +1, and so on. Okay, so let's see an example of a case where we actually end up with inference relations that no set of joint value assignments can satisfy. That can appear if our set has this form. So we have, again, just 2 qubits, but now we have X acting on each qubit and also Z acting on each qubit. Well, if we had a value assignment to S, then we could infer the values of the additional operators shown in these slightly larger trees. So each 3-vertex subtree here represents a single inference like we discussed in the last slide. So you can check that every parent node is the product of its children, and the children always commute. But in particular, we can infer from these trees if we just follow, like there's a plus or minus value assigned to each of the leaves in each of the trees, and we can follow the products of those values up the tree and infer that the value assigned to plus yy over here and minus yy must both be the products of the values assigned to the operators in the original set, since those are the leaves in each tree. Now, this is clearly a problem because we can't have plus yy and minus yy assigned to the same value unless that were 0, which is disallowed. It has to be plus or minus 1. So this means that any assignment of values to these trees must violate at least one inference relation in one of the trees. One of the little subtrees must be violated. So this implies that the set S is contextual. And I should note that this example is just, this is a recasting of the Perez-Mermin square, which is one of the classic examples of strong contextuality. So this is, again, not new, but it's a little bit of a different way of looking at it. Now, on the next slide, I will show you one of the first main result, the conclusion of this first section of the talk, which is a necessary and sufficient condition for contextuality of any arbitrary set of Pauli operators. But first, I just want to highlight one common misconception about contextuality. Probably this isn't tripping any of you up, but it has happened often enough that I just want to highlight it. I have said that a non-contextual set of observables permits consistent joint value assignments in the sense that they satisfy all inference relations. But that does not mean that those joint value assignments are physically realizable. We're used to talking about commuting sets of observables as those that can have definite values simultaneously. This means that they have joint eigenstates. So you have physical states that actually realize the joint value assignments in that case. But with contextuality, we're talking about a broader notion where we're not asking whether there exists a joint eigenstate. We're just asking whether there's any logical contradiction in assigning the joint values. If there is a joint eigenstate, meaning if the observables commute, then that state actually realizes a joint value assignment. So clearly in that case, there's no logical contradiction. So commuting implies non-contextual, but the reverse implication is not true. And an example is the single qubit non-contextual model that we talked about a couple slides ago, because there are all 3 single qubit Paulis anti-commute, and yet the set of them is non-contextual. Any questions about contextuality so far? Basic picture. Okay, shout it out, stop me if something is confusing. Anybody? Okay. So yeah, that brings us to our first main result. This is a necessary and sufficient condition for contextuality of any set of Pauli operators. And we're actually going to focus on the non-contextual case for the next section of the talk. So I'm going to put it in that language. And I'm not going to go through the proof of this here for the sake of time, but a set S of Pauli operators turns out to be non-contextual if and only if it has this form. So what's going on here? Well, first of all, there's allowed to be a subset of S that I'm calling script Z, such that every operator in script Z commutes with every other operator in S. So it's sort of a universally commuting part of the non-contextual set. And then in whatever the remainder of S is, which I'm calling T, commutation is an equivalence relation, if and only if the set is non-contextual. So if it's an equivalence relation, then it has equivalence classes, and that's what these C's are. So each C is an equivalence class of commutation within T, so not including the universally commuting part. So that just means that Paulis in the same subset C, all of the Paulis within this subset commute with each other, but they anti-commute with any Pauli in any of the other subsets. So non-contextual sets of Pauli operators are exactly those with this form. And here are a couple of examples. First of all, as we just said, any commuting set of Pauli operators is non-contextual. We can think of that as the cases where there's no subset T, there's just the subset Z that commutes with everything. But also any fully anti-commuting set of Pauli operators is non-contextual. In this case, we can think of there being no fully commuting subset Z, there's just T, and actually none of the operators commute, so each one is in its own equivalence class. So in that case, each of these equivalence classes would only contain one operator. There's one for each operator. That's the anti-commuting case. And that includes the single qubit case. So each X, Y, and Z would be in its own equivalence class. And finally, more generally, but not quite most generally, any set in which commutation is an equivalence relation, even if the equivalence classes have size larger than 1, is non-contextual. So that's just the general case when there's no subset Z. So here's an example of that. Each pair within parentheses commute with each other, but they anti-commute with any operator in a different pair. So since S defines the set of measurements that we're performing on the quantum computer in the Vqb algorithm, we define the VQE instance and the associated Hamiltonian to be non-contextual if and only if S is non-contextual. Okay, so that's bringing me to the end of the first section of this talk. This is our condition for non-contextuality of a VQE instance. Okay, so given this condition for non-contextuality, and given some non-contextual Hamiltonian, suppose we have some non-contextual Hamiltonian, so it has that form that we just talked about, we'd like to be able to actually construct the classical hidden variable model from it. We know that we should be able to, so we should actually do this. And we can start by constructing a reduced non-contextual set, starting from the original set and paring it down into a set from which we can recover the original set of terms in the Hamiltonian by inferences. So we know that if it's non-contextual, doing these inferences will never give us any problems. And so we're going to try to pare down our set into something that we can get back the full set from inference. That's this set shown here. And I'll explain this in just a minute. But its key feature, in addition to being able to reconstruct the Hamiltonian by inference, is that this set should be independent, meaning no value of any operator in this set can be inferred from the value of, or the values of any other subset of operators in the set. This will mean that all joint value assignments to this set are allowed, since there are no constraints on them coming from inference relations. So if we think back to our example of single qubits, X acting on each of a pair of qubits, those two operators together, the single qubit X's, are an independent set. But if we were to add in the XX as well, then the whole set of 3 is no longer independent because any one of them, the value can be inferred from the other 2. So if this set is independent, since we can recover our joint value assignments to the whole Hamiltonian from this set, this provides a simple way to enumerate those because all joint value assignments to this are allowed. And if you want a slightly more formal definition of this independence, you can say it's independent under the Jordan product, which is a half times the commutator, but that's not so important for us. So what are these objects here in this set? G is an independent generating set for Z, which if you remember was the fully commuting part of the non-contextual Hamiltonian. So this is an independent generating set in the sense of an abelian group. So under the regular matrix product. And then the remaining objects here, these A sub i's, are just one object from one element, one Pauli operator from each of the commutation equivalence classes, C sub I. And again, I'm not going to prove this, but it turns out that every term in the non-contextual Hamiltonian is equal to some commuting product of a subset of these. So that means some product of generators in G, which I'm calling G sub j's, with just one of these, since these don't commute with each other, or either one or none of these. And so we can express the Hamiltonian in that form. B is just a product of some subset of G. So there's a term that's just B potentially in the Hamiltonian. This would correspond to an element of Z, the fully commuting part. And then there's one term for each product of B with one of the A sub i's. And these coefficients are just the same coefficients as in the original Hamiltonian under convenient relabeling. All of this is efficiently classically calculable. And it might be also that some of these coefficients are 0. So not all of these terms have to be present, but this is the most general form. So at this point, we've fully described the joint value assignments in our classical model. And we've shown how the Hamiltonian is related to these generators that are giving us the joint value assignments. And the details of what I've described are, again, they're not too important, but the main point is that we have a way of enumerating these joint value assignments now, as well as a map from those points to values of the Hamiltonian given by this function. So all that remains is to describe the probability distributions over these value assignments that correspond to valid physical states. And for this purpose, or for our purpose in this work, we just want to generate expectation values of the Hamiltonian. That's our whole goal here, because we're just trying to classically reproduce the objective function in the Vqb optimization. And for this, it turns out that it's enough to allow this particular set of joint expectation values for the generators in our set. So these G sub j's, again, are just the elements of G. And these joint expectation values, so meaning it would be an assignment of an expectation value to all of the G's and all of the A's at once. Such an assignment corresponds to a joint probability distribution that's just a little bit more complicated to write down, but it would be the product of the marginals corresponding to these expectation values. So what we're doing here is we're assigning definite eigenvalues plus or minus 1 to each commuting generator G sub j, and asserting that the expectation values of the A sub i's have to lie on a unit sphere of the appropriate dimension. So R is a unit vector of dimension n, because there's n A sub i's. And yeah, I'm not going to prove this, but it turns out that these joint expectation values are sufficient to recover every possible expectation value of the non-contextual Hamiltonian. Okay, so now we can insert these parameterized expectation values back into the Hamiltonian to obtain a parameterization of the Hamiltonian expectation value. So I've taken that form from map for the Hamiltonian function from the previous slide and just replaced the operators with their value assignments. This works only because the expectation values assigned to the commuting generators are plus or minus 1. In general, an expectation value of a product is not equal to the product of the expectation values, but in this special case, it is. And there turns out to be at most 2n plus 1 of these parameters in total, so elements of Q and R. So this expression is an objective function of order n real parameters that can reproduce all expectation values of the Hamiltonian, again, strictly in the non-contextual case. So one immediate consequence of this is that it provides a dequantization that I'm putting in quotes of non-contextual VQE. So why am I putting this in quotes? We're replacing the quantum part of the procedure with a classical objective function. This does not prove that there can't still be some quantum advantage for non-contextual VQE, because there could be some clever way to use the NZS preparation to get an advantage. So the takeaway of this point is that in the case of non-contextual VQE, instead of doing a quantum simulation of a quantum system, we're really doing something that looks more like QAOA. So we're doing quantum simulation of a problem that is sort of masquerading as a quantum problem, but it's really sort of essentially classical because we can express it in terms of a classical objective function. And the second closely related conclusion is that the non-contextual Hamiltonian problem is an NP. So this is think of the local Hamiltonian problem. We're trying to bound, it's the decision problem of whether the ground state energy is above or below some promised gap. This follows because any possible energy that the Hamiltonian can have is associated to some parameter setting. And that parameter setting together with this objective function serve as a classical witness for that energy. So there's some details into showing that this is really true, but that's the basic idea. So that basically wraps up the case when the Hamiltonian is non-contextual. So what if we're given a Hamiltonian that's contextual though? This is true in general. And it turns out that for many quantum, I might even go so far as to say most quantum systems of interest, it appears to be true for all of the interesting cases, meaning the Hamiltonian is contextual. So for example, for molecules, the only system that I know of that's completely non-contextual is H2 in a minimal basis. All of the other molecular electronic structure Hamiltonians that I know of are contextual. So we'd like something that can apply to this case. But we know that if the Hamiltonian is contextual, we can't build a classical model of the kind that we've been talking about. So what we can do instead is we can try to partition the Hamiltonian into a non-contextual part and whatever terms are left over, which will in general be a contextual set. And we can try to choose the non-contextual part of the Hamiltonian to be as large as possible, according to a definition of largeness of our choice. And then we can use our classical method to approximate the ground state energy of the non-contextual part. So just optimizing that objective function from the last slide. And we can take that as a purely classical first approximation to the ground state energy of the full Hamiltonian. So we're essentially just ignoring this contextual part and using only the non-contextual part. Unsurprisingly, I think this doesn't work that well in practice. So if we have access to some quantum resources in addition to our classical resources, we might want to get those involved to maybe make this approximation better. And it turns out that we can use them to find a quantum correction to the non-contextual classical approximation that at least partly accounts for the remaining contextual terms. So how do we do this? Well, the energy minimizing parameter setting is some QR. You can think of this as the non-contextual ground state, although it's not a quantum state, it's just some parameter setting. This corresponds to some subspace of quantum states, actually. And this subspace turns out to look quite a bit like a stabilizer subspace, just where one of the stabilizing Pauli operators has been rotated by some unitary that preserves the other stabilizers. So I'll describe this subspace a bit more carefully momentarily, but first, what we're going to be able to do with this is obtain a contextual correction by minimizing the energy of the contextual part of the Hamiltonian within that subspace, this sort of quasi-stabilizer subspace. And we would do this using an actual quantum Vqb algorithm that's just restricted to that subspace. So let me explain more carefully what this subspace is. Again, the G sub j's are just the Pauli operators that are generating the commuting part of the non-contextual Hamiltonian. And we are assigning, our parameter assignment directly assigns eigenvalues to these. So the quantum states consistent with the non-contextual ground state have to live in the corresponding common eigenspace of the G sub j's. And they turn out to also live in the +1 eigenspace of this operator script A, which is a linear combination of the A sub I generators. These are the ones that are coming from the anti-commuting part, or the equivalence relation part of the non-contextual Hamiltonian. And they're weighted by their expectation values as given by these parameters R. So if you recall, R is a unit vector, and this is a normalized real linear combination of anti-commuting Pauli operators, and such a thing is unitarily equivalent to a single Pauli operator. So script A is this Pauli stabilizer that's rotated by a unitary, if you want to think about it that way. So it has eigenvalues ±1, and the subspace we're interested in is its +1 eigenspace. And we can show that the unitary that rotates this to a single Pauli operator commutes with the other stabilizers, so it's not messing them up in any way. So putting this all together, we're assembling our expectation value for the full Hamiltonian out of a non-contextual contribution that we're estimating classically by optimizing that objective function, and a contextual correction that we're estimating on the quantum processor. Now, when we restrict the contextual part of the Hamiltonian, this H sub C, to the subspace corresponding to the non-contextual ground state, it becomes simpler. And in fact, each non-contextual generator, which are, again, are kind of acting like stabilizers, each one removes 1 qubit's worth of freedom from the Hilbert space. So this contextual correction Hamiltonian becomes a Hamiltonian on the original number of qubits n minus the number of non-contextual generators, which is the size of G plus 1. So size of G for all of the G sub j's and plus 1 for script A. And also, fixing the values of the non-contextual generators effectively is imposing a symmetry on the contextual part of the Hamiltonian. So subsets of terms in this part also become equivalent to these symmetries. So generally, we expect the number of terms to also go down for the part that we're going to be estimating on the quantum processor. And here's an example of this. I'm not going to go through this, but we can come back to this if it's unclear. So I just said that the contextual correction Hamiltonian, which is the Hamiltonian that we actually have to do the quantum part of the algorithm on, is on a number of qubits that's given by the original number minus the number of these non-contextual generators. But what if we have access to more qubits than that? Maybe we would want to use these in some way to improve our accuracy too. If we do have more access to more qubits, then what we can do is we can just leave some of the non-contextual generators and the terms that they generate in the contextual part of the Hamiltonian. So in that case, we would be reducing the size of the non-contextual part in exchange for simulating more of the Hamiltonian on the quantum processor. So this is going to strictly expand the quantum search space. Every stabilizer that we move back into the contextual part adds 1 qubit to the quantum part of the problem. So this can't make our approximation worse. We could always go, this includes the states where the value of that qubit is fixed. And at some point it has to make it better, because in the limit where we just take the whole non-contextual Hamiltonian and put it into the quantum part that we're simulating on the quantum computer, that's just giving us back regular Vqb, where we're minimizing the energy of the whole Hamiltonian on the quantum computer. And that, if we search over assume we can search over the whole space for that, that should find the true ground state. So in this way, we can use our additional qubits on the quantum computer to gain accuracy. And certainly there's a degree, there's a question of expressibility of the ansatz to worry about here as well. That's something that Tim and Alexei have spent some time working on. But it's not really different from the same question in regular Vqb. And I'll talk about that a little bit more in a couple of slides as well. But to sum up this sort of theory chunk, we refer to this collection of ideas as contextual subspace Vqb, or CSVQE, because this quantum search space, in some sense, is the contextual subspace that encodes the degrees of freedom that are left over after we've fixed the non-contextual part. So finally, since CSVQE, like VQE, is a it looks like I didn't advance my slide. That makes sense. Sorry. I want this slide now. Yeah, so this is a heuristic algorithm, is what I was starting to say. And these graphs here are showing how it performs on a collection of electronic structured Hamiltonians corresponding to these various species of molecules. Unless they're stated otherwise, the bases are STO3G. So each curve is corresponding to a particular one of these molecules or atoms. The x-axis in each plot is the number of qubits that we're using on the quantum computer, and the y-axis is the overall error in Hartree in the ground state energy approximation. And all of these Hamiltonians, we first tapered off qubits using the classic qubit tapering paper that removes qubits based on symmetries of the Hamiltonian. So that's giving the total numbers of qubits that you see here. So the leftmost point in each one of these curves is in the 0 qubits column. That corresponds to the pure non-contextual approximation, where we're not simulating anything on the quantum computer. And then the rightmost point in each curve corresponds to simulating the whole tapered Hamiltonian on the quantum computer. And the black lines in each plot mark chemical accuracy. And I should note that the quantum parts of these algorithms we were solving by simulating by exact classical diagonalization, which is still tractable for these system sizes. So we're essentially giving the ideal performance of the algorithm here in the sense of assuming that it finds the optimal state with the lowest energy within the allowed subspace, within the contextual subspace, whatever that is. So the nice things that we see here are, first of all, as expected, using qubits generally gives you lower errors. Using more qubits, as we go to the right in these plots, they generally trend downward. And in most cases, we're reaching chemical accuracy before we are using all of the qubits that would be required for the full Hamiltonian. And in some of these larger molecules, this varies quite a bit, as you can see, but in some of them, it's pretty dramatic, which was nice to see. So the hope is that we can use this method to simulate larger molecules on smaller quantum computers while still getting results that are accurate enough to be useful. I have only one more substantive slide, but just as an aside, I also just want to point out that when we're reducing qubit requirements by any method, including this one, we do run a risk. Maybe risk is the wrong word, but we run a risk of reducing the problem so well that we don't need a quantum computer anymore. That's not reflected in these ones on this slide. All of these are small enough classically to begin with. But if we did do that, say reduce a 70 qubit problem to a 30 qubit problem, I have no idea if this is possible for any system, but that would be a nice result in its own right because it would yield a classically tractable method that is, sort of similar to active space methods. But from the quantum computing perspective, it's sort of not the ideal outcome. The ideal outcome is that as soon as we do have a quantum computer that's capable of running Vqb beyond classical simulability, so for a system size that's difficult or practically impossible to classically reproduce, we can use CSVQ to access a broader range of applications for it. And it also broadens the range of applications that are accessible for small proof of concept experiments, even if they are classically simulable. And yeah, this applies. This is something that I think is worth thinking about for any algorithms that are used to reduce, or any techniques that are used to reduce the qubit requirements for quantum algorithms. So now I just want to show this slide, which is coming from newer work that Alexi and Tim from UCL have worked on. They've carefully worked out how a lot of the details in this algorithm work, including how to take any ansatz you might want to use for the full Vqb problem and project it down into an ansatz for the contextual subspace. And this slide shows an example of that. These are results for essentially an adaptive version of the UCCSD ansatz, where gates are added successively based on the energy gradients that they yield. And then once the ansatz is constructed, we optimize the parameters as usual in Vqb. And these are noiseless wave function simulations, so still no noise, but we are doing an actual optimization now instead of exact diagonalization like on the previous slide. So on the x-axis, we've got iterations. This used BFGS optimizer, I think, and gate counts were up to around 20 gates for the larger molecules. And these are all for a particular size of the contextual subspace, meaning number of qubits for the contextual subspace, which are, it says how many qubits they are in the caption. And these sizes were chosen based on the results of the exact diagonalization to be where we expect to be able to, in principle, reach chemical accuracy. So it was nice to see that, at least for these small molecules, it seems to be working. Replacing the exact diagonalization with an actual optimization, we're still able to reach chemical accuracy, which is these dashed green lines are chemical accuracy. But of course, in the presence of noise, we might well expect some of these to fail. So that's one of the things that Alexi and Tim are working on as we're building up towards a demonstration of this method on an actual quantum processor. And these plots also, the takeaway is limited, I think, to some extent by the size of these molecules, which are still quite small and easy to simulate classically, but I think they're suggestive nonetheless. So we're working on pushing this to larger systems to see. So with that, here are our references for these results. And that's all I wanted to say. So thank you for your attention, and I'll be happy to answer any questions.
All right, thank you all. So like you've said, we have plenty of time for questions.
There's one in the chat.
Oh, yes, yes. So let's start off with.
Oh, I can find that. Okay, let me look. So the question is, sorry, do you want me to read it?
Yeah, go for it.
That'll help me to parse it anyway. For Hamiltonians that are entirely non-contextual, but for which we still hope to see some quantum advantage, such as diagonal Hamiltonians and combinatorial optimization, is there still a well-motivated partition into classical and quantum subsets of the Hamiltonian? Not in this way, because as the premise of the question suggests, they're non-contextual already. So this is quite right. Any diagonal Hamiltonian is non-contextual because it decomposes into tensor products of identity and Z. And typically it's explicit in these, like QAW, it's explicitly written in that form. I mean, the answer to the question is I don't know if there's a partition into classical and quantum subsets of the Hamiltonian. My guess is not, since the Hamiltonian is sort of explicitly classical to begin with. I would think of the whole Hamiltonian as classical, and any quantum advantage in that case has to come from the ansatz. I hope that answers the question. I suppose what you consider classical and quantum is somewhat a matter of opinion, but if it's a diagonal Hamiltonian, it looks pretty classical.
Yes.
Yeah, thanks for the nice talk, Will. This is Austin from Unit.
Oh, hi.
I hope you've inspired some people with contextuality Kool-Aid. But yeah, my question was kind of a little bit of a confusion regarding the use of strong contextuality here.
Right.
Because I mean, I imagine that since you want to in the end estimate some expectation values, you not only need to get possible values for the measured outcomes of how the operator is correct, but also the probabilities to measure those outcomes, right?
That's right.
Also, this notion of weak contextuality, which is to say that there are possibilistic assignments that I can give to each of the observables that I'm measuring, but I can't actually match the probabilities.
That's right.
One example that, while you were talking, that's maybe a good example, but also a bad example that I was thinking of, is a Hamiltonian that's just something like the CHSH Bell operator, right?
Right.
So any local hidden variable theory would tell you that the lower bound of the ground state energy, so to speak, would be 2, or I mean -2, I guess, if I put a minus sign in front. But quantum mechanically, right, the ground state energy would be -2. Yeah, so I'm just wondering, like, yeah.
Sorry, can you repeat the last sentence? There was a sound that.
Oh yeah, it's just the fact that for the CHSH operator, right, both hidden variable theories could be 2, but quantum theory could be 2√2 for its identification.
Right.
Right. So I'm just kind of curious whether or not, like, to what extent, I guess strong contextuality is sufficient in order to do the contextual subspace Vqb, or are there ever times where I need to think about, this notion of weak contextuality, since like estimating expectation values still might be hard. You can't quite get those probabilities right with the local theory.
Right. Well, I would need to sit down and look at how this works for the CHSH Hamiltonian, but what is indeed true is that if you have a non-contextual Hamiltonian, you can always express it as a classical function of this form. And this classical function can actually cover every possible expectation value of the Hamiltonian. So I'm not sure what breaks the argument that you just made.
Yeah, I mean, I guess in the end, like, maybe you have some, like, are you also taking the condition that whenever I take some context combinations of these classical assignments that you're putting on the Hamiltonian, that I can actually look over joint probabilities for the different assignments and we don't have this condition that the probability necessarily needs to factorize amongst the different observables? The different, sorry, I guess like.
Sorry, can you say again?
Yeah, is there, so I mean, I imagine at the end you have some value that you get whenever you just plug in plus ones and minus ones. I mean, I guess in this algorithm, in this classical optimization that you're doing, you search over probability distributions too, like taking some context combinations of these different classical assignments that I get.
That's right. That's right. So that's what these things correspond to. These parameters correspond to assignments of expectation values to the generators, essentially. So what that gives us is effectively this is a way of parameterizing a joint probability distribution.
I see. Okay, so it can be a joint. It's not the case with probability distribution. It's a factor amongst different individual, I guess, sites that you will.
That's right.
Okay.
Yeah. Yeah. There's no constraint of that kind. Yeah, so this is what, yeah, this is a subtle point though. It's quite a special case that here strong non-contextuality means that we can build the whole hidden variable model. Austin's quite right to point out that this is not true in general.
Cool, thank you.
There's another question in the chat. Maybe I will read this one because I think it came in right after Austin started. So the question is, it seems that your approach could suggest that there could be a notion of more or less contextual. Does a notion of the amount of contextuality already exist? And have you thought about such formalism? Yes to both questions. There's a bunch of different notions of amount of contextuality in a sort of similar way to there's a bunch of different notions of amount of entanglement. There's a number of different measures. I've thought about this a little bit, and we talked about this in the very first paper, this one, where we were just deriving the if and only if condition. And so, a simple measure of amount of contextuality that we could write down based on our notion of contextuality, our criterion, is take your Hamiltonian, find the largest non-contextual sub-Hamiltonian, or let me go back a couple slides. So take our Hamiltonian, find the largest possible non-contextual sub-Hamiltonian, and then your measure of contextuality is a norm of your choice on whatever is left over, the contextual part of the Hamiltonian. And so this is when I said that H2 in STO3G basis is non-contextual, that means that this HC is strictly 0 in that case. But there are actually a number of other small molecules where HC is not strictly 0, but it's very small. So that's actually where a notion like what you've just suggested can be actually useful to sort of predict how quickly we should be able to get to very low error in these plots. Yeah, it's a good question.
All right, we have a question from Andrew.
Yeah, so in fact, on this plot, all of your errors go negative at some point. I'm just wondering, is that related to contextuality or?
So this is a little bit misleading. Sorry, these black lines are not at 0, they're at chemical accuracy. So they're actually going to 0 error by the rightmost point. They're not actually negative. So it's just that on the scale of these plots, chemical accuracy appears quite close to 0 to the eye. Let me zoom, maybe I can zoom in on one of these. Yeah, like this first. Yeah. Good question. Yeah, sorry, that's probably a little bit hard to see there.
Well, so then the black line is what?
It's chemical accuracy, so it's
Okay.
0.0016 Hartree. So generally speaking, chemical accuracy is just kind of a rule of thumb for if you can get ground state energies that accurate, you can predict molecular dynamics roughly within an order of magnitude.
Okay, so the fact that you're under all those black lines is a good thing.
This is a good thing, yes, but it's not negative error. Yeah, that would be concerning. There's another. Oh yeah, no, nothing else in the chat.
Other questions? Yes.
Oh, there is one more in the chat. Sorry, is there somebody in the room?
The chat can go first, I guess.
Okay, so Susie in the chat says, is there a direct or intuitive relationship between a spatial electron correlation in the sense of beyond Hartree-Fock and the definition of your own non-contextual Hamiltonian terms? This is a great question. And the answer depends on the choice of the non-contextual Hamiltonian. The Hartree-Fock Hamiltonian is diagonal, so it is non-contextual. And you can actually take the Hartree-Fock Hamiltonian and add basically one excitation plus the associated number excitations, one single excitation plus the associated number excitations to it, and it will remain non-contextual. So in that sense, we can get slightly beyond Hartree-Fock. I mean, explicitly a little bit beyond Hartree-Fock while remaining non-contextual. But probably obviously a single excitation plus the number excitations, there's a lot more to the electron correlation than just that. And so actually, if we choose the non-contextual Hamiltonian in that way, beyond Hartree-Fock and contextual are quite similar, because the maximal non-contextual Hamiltonian of that form and the Hartree-Fock Hamiltonian are pretty similar. The non-contextual Hamiltonian just gives you a little bit more on the classical side. But you could also choose the non-contextual Hamiltonian to be something of a completely different structure that doesn't look anything like Hartree-Fock. So that could give you something that has lots of, a bunch of double excitations in it, say, but then it would have to not have some of the number terms or something like this. There's a lot of structure in the electronic structure Hamiltonian that we've actually sort of gone through and classified the different types of non-contextual Hamiltonians that can show up. This is as yet unpublished work, but it will be coming out. So this is the kind of thing that we're interested in trying to think about. Yeah.
All right, next question.
Hi, I'm Jun from UNM. I'm a postdoc. I think if I remember you, we had a beer at QIP, but I'm really bad at remembering people. So were you there at QIP?
Yes.
Okay, then we probably did grab a beer. Anyway, hi.
Hi.
Yeah, I was wondering, I guess this decomposition into the non-contextual and contextual part really makes sense especially when you think about these quantum chemistry and molecules that are like relatively small. I was wondering if there's like a non-trivial example with something like a condensed matter system Hamiltonian.
Sorry, can you? A what?
A condensed matter kind of Hamiltonian. So because I was trying to make sense what happens, for example, when you think about the transverse field Ising model, which is pretty much the easiest example, and also is in many ways almost classical because you can map it to a one-dimensional classical Ising model. But it seems like when you're doing this kind of decomposition, you're always kind of bound to get the non-contextual part to be just be the Z basis part, or maybe the X basis.
Yes, this is exactly right. Yep.
So I was wondering if there's like a more non-trivial example where you, I don't know, get some kind of a interesting decomposition by looking into the maximal non-contextual part, or good
question. This is something that I have thought about a little bit. So as you say, for the Ising model, you can you actually basically have two choices. You can choose all of the z terms. Well, okay, maybe there's three choices. You can, choice number one is you can choose all of the z terms and one xx term. Choice number two is you can choose all of the x terms and one z term. And choice number three is sort of breaking it up into cells that are doing some combination
Or
of
maybe
both.
like the left half and the right half or something.
Yeah, exactly. You can do things like that. Basically, none of these cases I would expect the non-contextual approximation to do well. I mean, you're essentially choosing a phase in some sense. And so something near the phase transition, it's not going to do well. And I haven't done a comprehensive look at other condensed matter Hamiltonians to think. We've mainly focused on chemistry. My guess is that we're going to get similar kinds of issues, which would mean that basically I'm guessing that the non-contextual part as an approximation by itself is not going to do very well in these systems. The reason for that is that this is really at the level of rough intuition, but in chemistry Hamiltonians, you have many different energy scales. And so you can get a pretty good approximation by only capturing some of these energy scales and maybe part of another one. But in a condensed matter Hamiltonian where you have, you know, a lot of terms acting on giving you interactions between qubits all at roughly the same strength, this looks worse for this method. Yeah.
Thanks. Yeah.
Yeah. Good question.
Thanks. Yeah, I was reading your papers a while ago actually, and I was trying to think if to come up with a condensed matter, you know, not trivial example, but yeah, it's good to know that you also kind of.
Yeah, I also haven't come up with one where the non-contextual part does well.
All right, thank you so much.
Yeah, sure.
All right, next, one more question, Carol?
I will very nice now. So I have a question. So how you define chemical accuracy? This is, I presume, you define chemical accuracy for with respect to the exact solution of the Schrödinger equation for CI within a given basis set. Is that right?
Sorry, can you say the question again? It's a little bit hard.
How you define chemical accuracy with respect to what energy?
How do I define accuracy here?
Yeah. So
Yes, full.
What are you using for? What energy are you using for the calibration?
The exact ground state energy calculated by classical diagonalization of the Hamiltonian in the particular basis. So again, these are all
for the same basis. Okay, thanks.
Yeah. So yeah, same basis. So like this would be, this red curve is H2O in the STO3G basis, and all of these errors are relative to exactly diagonalizing H2O in the STO3G basis. So doing this, making this kind of plot for examples much larger than this will become hard to impossible. This is purely for the purpose of demonstrating, you know, for small systems, we can get the exact error. So that's what we're looking at. Good question.
Any more questions for Will? All right, then let's thank Will again. Take a little break now, and we're going to be back here at 3:30 to discuss materials and algorithms. And Will, you're definitely invited to come stay, join us again at the discussion.
Thank you.
If you're able to. All right, thank you. Great.
Yeah. I just want to, we need to stop recording here. Yeah, that's what we're trying to do. We need to mute it. Yeah. Yeah, it's over here. That's a gorgeous.